So in today's tutorial, we're going to be speaking about quantum numbers. And in a very simplistic definition, quantum numbers are actually a set of four numbers that are going to describe the position for an electron in an electron cloud in Schrodinger's atomic model. And they're basically going to give us some characteristics that reveal information about the element or the atom in question. So starting very briefly, we have four different ones, and I'm going to use color coding for this. So N is also known as the main quantum number, and it's also synonymous to saying shell, valence shell, energy level, and it also corresponds to the period on the periodic table where our actual atom or element is located. So having said this, the possible values for main quantum number are integer values 1, 2, 3, 4, 5, 6, and 7, which up to today are basically the known periods in the periodic table. So remember, periods are those horizontal rows in the periodic table. Then we have L, which is called the azimuthal quantum number. And the azimuthal quantum number is also synonymous to speaking about orbital shape. In other words, it tells us what type of orbital we're on. Our last electron, what orbital shape it's on. So if we remember the orbital shapes, they're S, P, D, and F. And these numbers are going to correspond to specific, these letters are going to correspond to specific integers. Okay, so remember, S is sphere orbitals, P is dumbbell-shaped orbitals, D is that flower kind of shamrock shape, and F is really difficult to draw. So we're going to leave it at that. But some of the possible values for this is S is always 0, P corresponds to number 1, D corresponds to number 2, and F corresponds to number 3. So we have spoken about two of those different quantum numbers. Now, when we speak about M is the magnetic quantum number, okay? And this can also be synonym of orientation. So this means how the orbital itself, how the L number, which is the pink one that we drew, is actually oriented in space. And for this, we can take the example of a p orbital. So if I draw my axes right here, x, y, z, for example, we're going to know that, remember, p orbitals have three different orientations, and they rest on the different axes. So then when we put this orbital together, this is a whole p orbital. But remember that each orbital is going to hold 2 electrons. So in this case, p can hold 6 electrons. And if we remember from our other videos, and I recommend that you watch the electron configuration videos, remember that S can hold 2 electrons, P can hold 6 electrons, D can hold 10 electrons, F can hold 14 electrons, meaning that there's only one orientation. There's 3 orientations for P, just like we showed right here. 3 different ones, 1, 2, 3. And each of them holds 2 electrons. And that means that for D, there are 5 orientations. And for F, there's going to be 7 orientations. So in this case, we can draw a little diagram. And we can say, if we're SPDF, S, P, D, and F, our orientations are going to be these little boxes that I'm going to draw, right? So 1 orientation, P has 3 orientations, D has 5 orientations, and F is going to have 7 orientations, right? And the way we actually assign the number values is quite straightforward. If we only have one box or one orbital orientation, the number is going to be 0. If we have 3 boxes, our boxes in the middle are always 0. So then, like if it was math, we go to number 1, and what's the other side on the number line? -1. So 1, 2, -1, -2. 1, 2, 3, -1, -2, -3. And These are all the values that the magnetic quantum number can have depending on what orbital you're on, okay? So if you're in s orbital, it can be 0. It can only be 0. If you're in p, depending what is the last electron you drew, it's -1, 0, or 1. If it's d, so forth, right? So remember this little pyramid. It's a good way to remember what we're looking at. Last but not least, let's speak about the spin quantum number. And the spin quantum number is very straightforward. The spin quantum number is only going to tell us the direction in which the electrons are spinning. And this is not up or down, left or right, it's just relative, right? So the direction can be upward or downward when we draw our little diagram of orbitals. And this is represented as, if it's an upspin electron, it's going to be positive 1/2. And if it's a negative spin, negative 1/2. So we're going to have very specific combinations of numbers. Some number combinations are not possible. We'll speak about that in a few moments. But let's look at a concrete example, okay? So let's take carbon. Carbon has atomic number 6. So that means that if we make our electron configuration, we go 1s2, 2s2, and we're still missing 2 atoms, right? And those two, not 2 atoms, I'm sorry, 2 electrons, are going to be on 2p2. P can hold 6, but we only need 2 spaces. So let's look at that last orbital that we're filling. If we transform this into our diagram of orbitals, we draw our little boxes for the p orbital. All of this is named 2p. And then we arrange the electrons on the valence shell. So we need 1 and 2. So remember, electrons are always filled left to right, up, 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 down, down, down. However, in this case, since we only have 2, they're both going up, okay? Let me draw on the other side. We're going to draw here 2s. 2s is only one box. It only has one orientation, just like in this previous example I showed you right here. So those electrons that we have, I'm just going to draw the whole thing, you guys. 1s, here we have our box. So I drew my electrons, up spin, these two, up and down, up and down, up, up, and those are our 6 electrons. 6 electrons, okay? Now, what we're looking at is the last electron we filled. That's usually the one we're focusing on. So in this case, it's this guy right here. So, as I said, and let's review, main quantum number, or principal quantum number, is the same as shell, the valence layer, the energy level, or the period on the table. And it can only be 1, 2, 3, 4, 5, 6, or 7, right? And we write them in this order. So, for this electron we're speaking about specifically, our first number is the same as the shell, as the valence shell, which is the highest number. So our number is going to be 2. Then for the second number, which is the magnetic quantum number is, for the azimuthal quantum number, we need to see if we're on an s orbital, p orbital, d orbital, or f orbital, right? So in this case, we are on a p orbital, and we know that p is always number 1. So we just write number 1, okay? Comma. Next is the magnetic quantum number, that as we spoke, is 3 orientations. We find the box we're on, and depending on the box we're on is the number we're going to grab. So here we're in the middle box, and the middle box is 0. So in this case, for this set of quantum numbers, the magnetic quantum number is 0. And last but not least, the spin. The electron is pointing upwards, so pointing upwards we have a positive 1/2. And this is how we assign quantum numbers to the different electron configuration that we have, okay? Now, let's look at another example. Maybe that was a little bit too quick. Let's go back. And let's just make up an electron configuration very simply. So we say, let's see, 1s2, 2s2, 2p6, 3s2, 3p5. So in total we have 17 electrons. So this is a 17 electron atom. And let's assume that it's neutral. So this is chlorine. Okay, you can check on your periodic table to see that that's right. So if we want to get the numbers for chlorine, we're going to look at the last orbital that was filled, which is 3p5. And remember, the whole orbital has a number, a coefficient, and a letter to describe the shape, and then a superscript to tell us the amount of electrons in it. So I'm going to focus on this one, and I'm just going to go ahead and write it. It's 3p, and if we remember, p orbitals have 3 boxes, right? So in this case, what I'm going to draw is I'm going to draw my up spins first. 1, 2, 3, and we want 5, right? So once we're done this way, because remember, electrons occupy the lowest energy level possible, and we require the spins to be even. So then we go back to the first box, 4 and 5. What is the last electron that we placed? The last electron that we placed, of course, you can see is this one, which I'm going to highlight in yellow. So that's the one we're going to base our quantum number assignments for. So remember, we open up some parentheses, some brackets, and our main quantum number, which is the same as the shell, we look at the highest energy level, it's 3, we just write a 3. Remember, values 1 through 7. Then for L, which is the azimuthal quantum number, we look at the shape. At the shape of what? The shape of the orbital, which in this case is P. Remember, S is 0, P is 1, D is 2, and F is 3. So we just look at this table, or we memorized it. Of course, we should have memorized it. And now we have for L, we have number 1. Continuing on, we need M, magnetic quantum number, which is the orientation. Other words, in what box, in what of the orientations that we fill our last electron. So in this case, since P has 3 boxes, 3 orientations, remember the middle box is always 0, and then the box to the right is 1, and then the box to the left is -1, like if it was a number line. So our yellow electron, the one we highlighted, is in box 0, so our magnetic quantum number is 0. And last but not least, was it an up spin or was it a down spin? Remember, up spins are positive 1/2, and down spins are negative 1/2. So in this case, our yellow electron is pointing down, negative 1/2. And right now would be a good moment to mention Pauli's exclusion principle, which means that no 2 electrons on the same atom can have the same set of quantum numbers. So let's do a little example. If I write this configuration, not this configuration, this set of quantum numbers, and I write plus 1/2, what electron are we speaking about? We're definitely on 3p because it's 3 and 1. We're definitely in the middle box, but what changes is plus sign. So this plus sign means that we're speaking about the upspin electron, which is this one, okay? So that way, each individual electron is going to have its own distinct configuration, okay? So, as I said, remember, try to watch some of the electron configuration videos, noble gases, and make sure you can look at these examples, okay?